The last objective in this section is solving applications of linear equations, right? What good are equations if we can't apply them to real life is what you're thinking, I'm sure. So to solve an application problem, we have to know what is the unknown and what is an equation that represents the situation. Then we'll solve the equation and determine how the solution applies to the problem. So I will work a couple of examples of these for you. So the first one is a young couple are planning their wedding. The venue they have selected charges a $1,000 rental fee plus a $50 per person catering fee. The couple has saved $12,000 for their reception, plus the maximum number of people that can attend the reception without going over their budget. So we need to think about what is the unknown in this problem. The unknown is the number of people that can attend the reception. So we will assign that unknown a variable. So we will say let x equal the number of guests. Then we need to think about how can we represent this situation in terms of an equation. So let's think, how do we get the total cost of the reception? Well, it is the rental fee plus the catering fee. And that will equal the cost of the reception. Well, our rental fee is a fixed cost, right? It doesn't matter if one person shows up or 100 people show up. The rental fee will be the same. So that's just going to be the $1,000 plus. Now, the catering fee is where it's a variable cost, right? Because that cost varies by the number of people that come. And the charge is $50 per person. X is the number of people. So our catering fee is really going to be 50 times the number of people X. That equals our total cost, which is $12,000. So now we can subtract 1,000 from each side to get 50x equals 11,000 and divide by 50. 11,000 divided by 50 is 220. So in this situation, 220 guests can attend the reception without going over the budget. Now, in some applications, we will already have a model that's given to us, and we'll talk more about writing models that represent situations later on through the course, but this one is according to data from the National Association of Theater Owners. The average annual price of a U.S. movie ticket can be approximated by P is equal to 0.19277x plus 3.428, where x is the number of years after 1989. According to this model, in what year will the annual average ticket price be $10? So in this case, we know this model, which is 0.19277x plus 3.428, and we know what we want the ticket price to be. We want it to be $10, which is our value of P. So in place of P, we're going to put 10. And now we can solve this equation for our variable x. We can subtract the 3.428 from each side and get 0.19277x equals 6.572. And then we can divide by the 0.19277. So x will equal 34.09 approximately. So how do we interpret this answer? Notice that the variable is x, which is the number of years after 1989. This therefore says that the average annual ticket price will be $10 in 34 years after 1989. To get the exact year, we can add 34 years to that base year of 1989, and that gives us the year 2023.